So now we've seen what the definition is of a ring. And the motivation, again, for what a ring is, comes from the usual arithmetic within the integers. The integers are an abelian group under addition, so we have the first operation, which has all kinds of nice properties. It has associativity, it has identity, it has inverses, and it also has commutativity, so addition. But then also, for the integers, we have a multiplication. That multiplication distributes over addition, which is something we definitely need, but that multiplication of integers also doesn't have certain properties. For instance, it doesn't have the invertibility property, because most integers, in fact, don't have multiplicative inverses that are also integers. But still, the integers are our prototype example of a ring, being an abelian group that has an additional operation on top of it that's associative and which distributes over the first. And that's all we need to make a ring. But we also saw in the last video some examples of rings that do have some of those additional properties with respect to their multiplication. We saw an example of the ring of integers that are multiples of 3, which had commutative multiplication, but which didn't have a multiplicative identity. We also saw an example of polynomials, which again had commutative operation and had a multiplicative identity, but most polynomials don't have a multiplicative inverse that is also a polynomial. So in this video we want to look at a couple more examples in a little bit more detail that illustrate some of the gray area in between having all the properties that we might want for a ring to have and having just the bare minimum of the properties that we want for a ring to have. We'll also see at the end of this video a classification of the different terms so that we can associate to rings based on the properties that they have. So we're going to start by looking at a very rich example called Hamilton's Quaternions. Now we've heard the name quaternion before in the context of group theory. In group theory, the quaternions are a group of order 8 that have the elements plus minus 1, plus minus I, plus minus j, and plus minus k. And those elements have a multiplication that is completely analogous to the multiplication that we get in three-dimensional cross products of unit vectors. Namely, I times j gives you k, and j times I gives you minus k. So we have this anti-commutative multiplication operation on the quaternion group. And what Hamilton's quaternions do is they take that multiplication and they turn it into a ring by making formal sums of i's, j's, k's, and constants, where the coefficients of those sums are real numbers. So Hamilton's quaternions actually look an awful lot like complex numbers, except that in addition to the imaginary unit I, we also have an imaginary unit j and an imaginary unit k. And each of them individually squares to -1, and that the multiplication I times j equals k, j times I equals minus k is anti-commutative. Then we just soup that up with real coefficients and we get a ring called Hamilton's quaternions. So as an example, what does multiplication look like in this ring? If I multiply 3 plus 4i times I minus 2k, well, because this multiplication has to distribute over addition, that means I can FOIL this product. So I'll get a total of 4 different terms by multiplying that out. And then simplifying these using the relations in the quaternion group, I find out that this product is 3i minus 6k minus 4 plus 8j. So that's how we multiply in the Hamilton's quaternion ring. Now this is not a commutative ring. The multiplication in this ring is definitely not commutative, and that's a simple consequence of the fact that even the multiplication of the unit quaternions, I, j, and k, is not commutative. So for sure, this is not a commutative ring. But we do have a multiplicative identity element. Namely, if I choose a equals 1 and b, c, and d equals 0, in other words, I make a real quaternion whose real part is equal to 1, then that's a multiplicative identity. That's not difficult to check at all. But what about inverses? Can I divide, in other words, in this quaternion ring? And an answer to that question is going to come from answering the question, if I have a quaternion a plus bi plus cj plus dk, what quaternion can I multiply that by in order that the product turns out to be 1? Well, we're going to try a trick that tends to work in a lot of different settings, and we'll see probably some deeper reasons for that this semester. And the trick is, let's try writing down the conjugate of this quaternion. Remember, the conjugate in complex numbers just trades out every I for a minus I. And so since we have 3 different imaginary units here, let's trade them all out for their opposites. So trade out I for minus I, j for minus j, k for minus k. If I multiply these 2 quaternions together, I'm going to get a whole bunch of terms, 16 of them in all. So I can write them all down just using the relations from the quaternion group to get them. But what you notice when you write down all these products is that everything with an I in it is going to cancel, everything with a j in it is going to cancel, everything with a k in it is going to cancel. And so the product of these 2 quaternions turns out to be the real number a squared plus b squared plus c squared plus d squared. And that's great news, because as long as a squared plus b squared plus c squared plus d squared is not 0, I can divide by it. And so the inverse of a plus bi plus cj plus dk exists and is equal to its conjugate divided by a squared plus b squared plus c squared plus d squared. So in other words, as long as that denominator there is not equal to 0, I can make an inverse for this quaternion, and this is any quaternion at all. So any non-zero quaternion has a multiplicative inverse, which is somehow really surprising. So this is a property that our rings haven't had up to this point, that everything besides the additive identity 0 has a multiplicative inverse in this ring. That also completely precludes the possibility of having any zero divisors. It's not too difficult to show that an invertible element, a multiplicatively invertible element of a ring, cannot be a zero divisor. So since everything that's not 0 is invertible, that means that everything that's not 0 is also not a zero divisor in this ring. So this is an example of a ring that has absolutely every property that we like, but it doesn't have commutativity. So we can have a ring that does everything except commute, which is kind of interesting. Hamilton's quaternions are interesting for a lot of reasons. Again, because of the connection to three-dimensional geometry, they provide a setting in which Hamilton, who came up with them in the first place, used them to do classical mechanics in 3 dimensions, so physics. We're interested in them for their algebraic structure, and they're a great example of a ring that is everything we could ever want it to be except commutative. And our final example is something that will be everything including commutative, the ring of rational numbers. Now, pay attention to this definition for just a minute on how we're defining what the rational numbers are. The rational numbers consist of all quotients of one integer by another integer, where the denominator integer q is not equal to 0. But we also have to impose an equivalence relation on top of that set that says that two fractions are equivalent if and only if their cross products are equal. So p over q is the same fraction as r over s if p times s is equal to q times r. So this is an equivalence relation definition of the rational numbers. It might be a little bit different than what you're used to. But under this definition, do we have commutative multiplication? Yes, we do. Do we have a multiplicative identity element? Yes, 1, which is equal to 1 over 1, is an identity element inside of q. We also have multiplicative inverses for everything that's not 0. If p and q are both non-zero, then p over q has multiplicative inverse q over p. So as long as p and q are both non-zero, then this will work. And again, having multiplicative inverses for all non-zero elements also precludes the possibility of having any zero divisors. So the rational numbers have everything on the menu. They're a ring with everything on it. The multiplication is commutative, there's a multiplicative identity element, everything besides 0, the additive identity, has a multiplicative inverse, and therefore there are no zero divisors. So this is an example of a ring that truly has every property we could ask for. So to finish up, what we want to do is just take stock of all the different properties that we were looking at with respect to rings and just kind of classify them together to figure out, first of all, which ones of them imply which others, and then attach some names to them so that we can refer to them later on in the course. So just a quick Venn diagram to finish this all up. So if I want to order a ring off of the menu, what am I going to call all of these different properties? So within the category of all rings, we have some rings for which the multiplication operation is commutative. Naturally, we're going to call those commutative rings. We also have some rings that have a multiplicative identity element. We're going to call those rings with unity. And we saw some examples in the past couple of videos of commutative rings that don't have a unity element, for instance, the integer multiples of 3. We also saw some rings with unity that were not commutative. So naturally, there's some overlap between these two categories of rings, but not all. So I'll put these as a Venn diagram with some overlap, but not a complete overlap. Then we had examples of rings in this video that had multiplicative inverses for all non-zero elements. We're going to call those division rings. Again, division just being the inverse operation to multiplication. And it turns out that in order to define an inverse in the first place, we need to have a unity, an identity element with respect to multiplication. So every division ring has to be a ring with unity. But as we saw in this video, not every division ring has to be commutative. Hamilton's quaternions were a division ring, but they weren't a commutative division ring. But it turns out that commutative division rings, like the rational numbers that we just saw on the previous slide, are the most special kind of ring that we can work with this semester. They have every property that we could ever ask for a ring to have. So we give those rings a special name. We call them fields. So a field is a ring that has all these properties. It's commutative, it has an identity element, and it has multiplicative inverses for all non-zero elements, which also implies it has no zero divisors. And those rings that have no zero divisors we're going to call integral domains. And as we saw, there are examples of rings that have no zero divisors which can be non-commutative. They might not have a unity element. But definitely, if we have a division ring, if we have multiplicative inverses for all non-zero elements, then we cannot have any zero divisors. So every division ring is definitely an integral domain. So there are all the different terms that we can lay on top of our study of rings. Ultimately, this semester, we're going to spend a lot more time studying rings with a lot of properties. In particular, we're going to be most interested in fields, because it's in fields where we're going to be able to study the solutions of polynomial equations this semester. But we are going to take a couple of more days and just dwell on rings for a little while, because studying rings can actually tell us something about polynomials themselves. And that's where we're going to go next, by looking at what kinds of sub-objects live inside of rings. Those are called the ideals.